this video, I wanted to talk about balanced growth paths in the context of the augmented Solow model. The aim of the video is twofold: first to introduce the concept of balanced growth paths in an economy, and then show you how to compute this BGP in the context of the Solow model, in which we introduce labor augmenting technology. First, let me remind you the basics of the Solow growth model with labor augmenting technology. So we'll say that technology, which is denoted by AT, is labor augmenting if production can be written in a very specific way. That is, YT, GDP, is a function of KT, physical capital on the one side, and AT times LT as a second argument, with F a constant returns to scale production function. If technology is labor augmenting, if it applies to labor, then we can define another variable, which we'll call efficient labor, and that's simply defined as the product of labor by technology. With this definition of L tilde T, we'll basically represent the fact that we consider that technology acts as if it was multiplying the number of workers in this economy. In the case of the augmented Solow model, population LT and technology AT both grow at an exogenous constant rate. So A, the technology, grows at a rate G, and L grows at a rate N. In this case, the efficient labor will grow at a constant rate as well, which is the sum of the growth rates of these two variables. So delta L tilde T over L tilde T equals G plus N. Now, in this augmented Solow model, our state variable will be the amount of capital which is available per efficient worker, defined as K tilde T equals aggregate capital KT divided by L tilde. So we have a law of motion for this K tilde variable, which is as follows: delta K tilde T is equal to delta KT over L tilde T minus this dilution term N plus G K tilde T. Now, if we use the law of motion for aggregate capital, we're able to rewrite delta K tilde T as equal to savings per efficient worker, SY tilde T, minus N plus G plus delta K tilde T, taking into account the capital depreciation. And using the expression for the production function, we can replace small y tilde T by F of K tilde T. In case you need some details about how to get this law of motion for K tilde, you can now go to the end of the video. Now that we have the law of motion for K tilde, we can look for the steady state of capital per efficient labor. So as we did in video 1, we're going to use the fact that this steady state is characterized by delta K tilde star is equal to 0, no variation in K tilde between two periods. This is equivalent to having the fact that savings per efficient worker as F of K tilde star is equal to the depreciation plus dilution effect N plus G plus delta times K tilde star. So this gives us a steady state for variable K tilde, but this also gives us a steady state for variable Y tilde, so Y tilde star, output per efficient labor. One thing we'd like to know though is whether this also gives us a steady state for output per worker and aggregate output. We'll see in what comes next that it's actually not a steady state, but something which is slightly different. We've now reached this second part of the video in which we get to talk more precisely about what a balanced growth path is. So let me start with a simple definition. We'll say that the economy is on a balanced growth path if all the relevant variables concerning this economy all grow at a constant rate. So I have to issue a word of warning first, in the sense that these different constant rates for the relevant variables of the economy absolutely don't need to be the same for all the variables. Some variable may grow at a slow rate, other at a faster rate, and some of them could even be constant, which means that the growth rate is equal to 0. Now, if we come back to the Solow growth model with labor-augmenting technology, we've seen just before that we can determine that there is a situation in which we reach a steady state for variable y tilde. So y tilde star is fixed, which means that this variable has a growth rate of 0. It's a constant. In this case, we can take a look at output per worker, small yt. You see that y tilde t is defined as yt divided by technology, so yt is equal to y tilde t times at, which means that in terms of growth rate, the growth rate of output per worker, delta y divided by y, is equal to the sum of the two growth rates, delta y tilde over y tilde, plus delta a over a, which means that in total, the growth rate of output per worker, delta y over y, is equal to 0 plus g, which means that it's equal to g, so also a constant. In a similar fashion, we can take a look at the growth rate for aggregate output. So you see here we'll use the fact that y tilde is big Y, so aggregate output divided by the number of efficient workers. So big YT is equal to y tilde times L tilde. Then the growth rate of big Y of aggregate output is the sum of the growth rate of y tilde and the growth rate of efficient labor. So this growth rate of aggregate output in this situation is equal to g plus n, so also a constant. What we've just shown is that basically we have three main variables for output, so aggregate output, output per worker, and output per efficient worker, which all grow at a constant rate in this specific situation, this steady state for variable y tilde. So all these variables grow at a constant rate, which is different. We could show in the same way that we have similar results for other variables such as capital, savings, consumption. So in this case, in the augmented Solow model, the economy will end up reaching a balanced growth path for which all variables grow at a constant rate. Alright, so you've now reached the end of the main part of this video about balanced growth paths in the augmented Solow model. One thing that I'll still show you in what comes next is how to get in some more details the law of motion for capital per efficient worker. Concerning the law of motion for k tilde t, I'm going to perform approximately the same steps that I showed you in video 1, so this is just a reminder here. The first thing we'll use is the fact that aggregate capital, big KT, is the product of k tilde t and L tilde t, and then we're going to use two things. First, the fact that the variation in capital, delta big KT, is approximately equal to the time derivative of k, so k dot of t, and then we're going to use the formula for the time derivative of a product of two different variables. So at this point, the only thing we have is a relationship between the variation of aggregate capital, delta big KT, and the variation of capital per efficient worker, delta k tilde t. What we want to do out of this is find the law of motion for k tilde, so we want to isolate delta k tilde. This is done as follows by dividing by L tilde t and putting everything that is not delta k tilde t on the right hand side of the equation. Another thing we can do to transform this expression is use the fact that L tilde is growing at a constant rate, a rate of n plus g. So this is done as follows. You can replace delta L tilde t over L tilde t by n plus g. And then to get to the end of the computation, we're going to use the law of motion of delta kt. So we know that the variation of big KT is savings, SYT, minus capital depreciation, delta KT. And then, as a last step, in order to get the final formula, we'll just divide YT by L tilde T, so we'll get small y tilde, and delta kt divided by L tilde t is simply delta k tilde t. So you get the final formula here. The variation in capital per efficient worker is made up of two different things. First, the savings per efficient worker, and then a second term that corresponds to capital depreciation and capital dilution.